So you might see an actual resistor in the circuit. Our wire is just represented by a straight line. And we've seen there how to represent our battery. We could also have like a power pack. And it might be represented like that. And we know that it's the power supply because it's got the positive and negative signs on the corners to tell us which end's which. Another thing that might be in our circuit diagrams is a switch. And I've drawn that to represent the circuit being open, and then if you close the switch, then our electrons are free to move. Just like if I have no battery or no power supply, the electrons won't move. Even if I have a battery and a power supply, if my circuit is open, like it is here, then the electrons won't move either. They can only all move, like they either no one can move in net movement, or everyone can move. And this is a good thing, that if we have the switch, that means we can turn off the light, we can turn off the heater, and we can turn off the kettle. All those things won't just keep going and going. So the switch breaks the circuit here, and all the electrons will stop. The electrons don't stop moving altogether, but they stop moving in the same direction. Now, if you open the circuit there, then their movements are manual. What we need to have for us to have current is for there to be a movement in one direction. Does that sort of sound okay, reasonable?
Just back to the whole lightning. Like, obviously I know that it's electricity, but where does it come from? Does it like use electrons in the sky, or?
Okay, yeah, so this was a circuit where I set it up with wires, etc. But lightning is what we would call static electricity. So if I've got a big cloud up here, just like with our Van de Graaff generator before, do you remember when we used the Van de Graaff pretty early in the year? Yep. And we were able to build up a charge on the big bulb by, and it was a positive charge we built up. We had the little bulb here, and it was getting a negative charge build-up. And the reason why we had this charge differential is because of the little brush on the belt, and it was scraping off electrons. One of the fundamental laws of physics here is that there has to be also conservation of our charge. And so whenever I generate, whenever I generate a positive charge somewhere, at the same moment I generate a negative charge as well, because overall there cannot be a build-up of a particular charge. and then they can come together and balance each other, and end up with no charge. But in certain circumstances, they're separated. And it could be, this is my cloud here, so it could be a storm or something like that. Sometimes there's dry lightning as well. But what we've got is, depending on the circumstances, we can have a build-up of charge. It could be windy. And at some point, more like that, isn't it? At some point, we'll have a discharge with lightning, where we even out the charges between the cloud and the ground. We can also have upward moving lightning, but it's the same driver. Is that at some point, just like with our Van de Graaff generator, when we build up the charge, build it up, until it gets so large that we end up with a spark happening between the two. It's the same with lightning. But what we've got is a build-up of charge between the cloud and the ground, or a build-up of a big enough charge difference between the cloud and the ground that it will discharge either down or up.
Does anything move? Does it any matter? What's the actual thing that we see? Is that just like the light energy?
Yeah, what we're seeing is light energy, yes. Because we're exciting the particles in the way of this energy. And with static electricity, it has very low current and very high voltage. So when I was talking to you about our circuit, we were thinking about a 12-volt battery or a 1.5 volt cell, and if we use the power points like we've got here, in Australia these are 240 volts. In the US they use 120 volts. But that's the sort of voltage we're thinking about for our everyday usage in a circuit. But we could have 5 million volts, or we can certainly have very big volts. We could have like 50,000 or 500,000 maybe even volts on our, probably go with 50,000. On our Van de Graaff generator, we can generate, static electricity generates a much, much higher voltage. And it's because of this, it's got to make its own path. In the circuit, there's the path already there. So the place for the electrons to travel is already determined. Whereas here, to jump between the big ball and the small ball, they have to make their own pathway through the air, and that's harder to do. And so we need to build up bigger potential difference between the two. Now, lightning does kill you, and because it is such a very high voltage, if you do get struck, it can be, there have been people who've been vaporized, literally, like all that's left of them is their shoes. So, you know how you're told that you shouldn't stand out under a big tree on a hill in a thunderstorm and all that kind of stuff? It's actually true. You shouldn't do that. And that thing about lightning never striking the same place twice is absolutely false. Lightning will strike wherever it finds the path of least resistance. And so the shorter distance here is going to, like if I had a tree here, then it's going to be likely to be struck because it's closer. And if you're standing there and there is no tree, you're going to get struck because you're going to then present the path with least risk, or a shorter path to travel. And if you're wet, then that also doesn't have notice. Apparently golfers are likely to get struck because they're out, you know, they play in all weathers, and they're out on the field, and there's rolling hills and stuff like that, and yeah, if they're out in that kind of weather, then they can also be struck. Now, not everybody is vaporised, thankfully, but certainly there have been a number of people who and it's very, very distressing for the other people around if somebody is basically struck with such a huge amount of energy and then they almost disappear.
Do different lightning bolts contain different voltages, or is it just like once they get to a certain
Yeah, all different. Yeah. It doesn't have to be a particular number.
Right.
All you need to know, I guess, is high.
Yeah.
Much higher than we actually see in our wiring in our houses and
Because surely they've looked at trying to like obtain electrical energy from lightning before, but surely
Yes.
it's just too much.
yeah, that's the thing. Is there certainly has been research into trying to harness the energy from lightning, but you need to be able to have something that can withstand that very high voltage and then store that energy. So you try and have something that can capture the energy without being destroyed itself. How we handle lightning at the moment, if you've got really tall buildings, so like skyscrapers, again, they're really big targets for lightning, aren't they? Because they're very, very closer to the clouds, and they will have a lightning rod on the top, and what that does is it provides a pathway to the earth, and the building is what we would call earth, so that the lightning rod is designed to attract that energy and then provide it with a pathway down to the ground where it's not going to be harmful. I don't know if you remember, probably too young, there was the whole thing of, there was an issue with people having their houses electrified through their insulation in the roofs. And how that happened was people in Queensland mainly were using like a metal foil to insulate their roofs, and sometimes the installers were accidentally like nailing that to the wiring, and then people's plumbing became electrified because the sheet of reflective layer in their roof was also sitting on top of the plumbing, and they would complain. They'd say, "Oh, you know, like I get a little tingle every time I turn on the tap," which is really, really dangerous. So electrons are going to find whatever path they can. If we've got conductors around there, then that's what's going to happen. They're going to conduct electricity.